Hello, this is James Whedon, and I'm going to present my embedded robotics final project today. So, the goal of this project was to essentially get an MSP 432 robot and give it all the directions it needs to follow a black line created by electrical tape across a otherwise white surface. Um, over here, I have a finite state machine that goes over all of the different transitions and outputs of the robot while it is driving across the track. So if we see here, um, I have um, well, first I have a start state, but after a user button press, they go into a centered state, which essentially is a representation of when the robot is directly over a black line, and then using LEDs that shine onto the surface it is on, it can then tell based on a reflected value whether it is directly on, to the left, to the right, or not at all on a black line. And using this information, we can determine whether um, the robot should turn left or right accordingly. So, looking out from this centered state, we can transition either to a left or right state, um, or if it is completely lost, a lost state over here. Um, so, this helps it go around a rudimentary track. But the problem is that it's easy to get lost and it's not very effective. So, adding on to this, additional states were added that essentially allow the robot to, uh, you know, go forward. If it gets a little off to the left, it tries to correct itself. But if it gets lost, it can actually go through an algorithm of taking a hard right or a hard left and going straight a little bit to try to get back to the path, which usually lets it recover without, just giving up and stopping. So additionally, with the motor driving, we also have lights that shine. The way the lights shine is encompassed in the FSM as well. Other inputs are also important to consider. So there is another concurrent finite state machine that I call the booster pack FSM, which takes two shared variables between the two, and sets a variable to determine whether the robot should, move slowly or stop moving. So, taking in from this added sensor from the booster pack information on whether it is accelerating past a certain threshold, or whether the amount of light that is detected by a sensor falls below a certain threshold. Um, we can determine whether the robot should drive slowly, maybe in dim, hazardous conditions, or whether it should stop at all because there is not enough light, or a bump switch was hit, or the robot was picked up, so its acceleration increased. Um, Using this along with the other FSM pretty much allow the robot to not only go across the track, but also have several ways to stop its movement in the case that you want to, check out its actions, or prevent it from getting damaged in less than ideal conditions. So moving forward from there, I just wanted to give a small demonstration of the code here. So um, over here, I have the actual C implementations of the finite state machines, um, going through each of these switch cases. So each of the cases represent the states of the finite state machines, in this case, the booster pack, um, taking in the variables, checking their values. Um, Not only do we have the state transitions, but also we have functions that can take in pointers to use references to variables and adjust them globally for the other finite state machine to see. Just going in here, we can also see the finite state machine for the driving FSM. Just to show a quick preview, based on the position values, we can adjust the motors to different speeds. And as you can see here, some of these values are divided by set slow. And the reason for that is that we set the set slow value in the booster pack FSM. And as you can see, if the FSM determines that it should transition to the take it slow case, then this value will change from 1 to 2, and we can essentially have the value of the motor speed. Going into this main class here, we essentially see how everything kind of meshes together. We have all these variable declarations. A lot of this was initialization for the booster pack, which had to initialize its gyroscope, structs for the acceleration values, and additional values for the OPT sensor that detected the amount of lux. And as you can see here, we actually take in these values and adjust them. So the accelerometer gives different values in X and Y directions, but to make the programming a little bit easier, I essentially just used the same example and kept the values converted to Excel good so that I could just read whether it has been determined that the acceleration is below or above a necessary threshold. Going back up here, there's also a task for the handler in which, based on this iterating count value, we can determine whether we should read the reflectance or the position or the bump value. Going here, we also have switch initialization so that to start the actual driving of the robot, a push button is pressed. So it just doesn't start driving the second you turn on the power. Going through here as well, we just have the initialization of the finite state machines in which the tasks can be put in and asynchronous inputs can be accepted. And that pretty much goes through the bulk of the main code. Now I will go through some demos of the robot driving, and yeah.